In this section, we will discuss about the integrated protection and integrated features of Texas Instruments high-side switch portfolio. The first protection mechanism that we shall discuss about is the integrated current limiting of high-side switches. A major concern for driving off-board loads are overcurrent events. These could be something as simple as driving a capacitive load, or something like a short to ground or a soft short to other voltage rails in the system. Current limiting protects the system during these events in two methods. The first is to clamp current at a specific value, and the second is to immediately turn off as soon as the current limit is triggered. This protects both the power supply from supply dips that could be dangerous to the rest of the system and high thermal events that could damage downstream loads. Integration of current limiting within the high-side switch reduces systems cost as well as solution size. Also, a choice is provided to the user. The user can use the internal current limit that is set at a high value, or can set an external adjustable limit using an external resistor. For integrated current limiting, there are two references. One of them is an internal reference for the internal current limit, and the other is an external reference that is built using the external current limiting resistor. Please note that the internal reference will always be larger than any external reference that can be set. Therefore, the maximum amount of current limit for a specific device is limited by its internal limit. Please find this internal limit listed in the datasheet for your specific device. Please note that the diagram on the right is for design reference only. The threshold voltage is maintained across the external resistor. Then, an internal proportional current using a current mirror is created and is compared against the threshold current, both internal as well as external. When this proportional current exceeds either one of the thresholds, the current limit is set to be hit. This results in two operations depending on the type of device you have. The device can either immediately turn off in the event of immediate shutdown devices, or can result in current clamping in the event of using current clamping devices. The gate charge is changed and regulated so as to increase the VDS. This results in the device becoming a constant current source. Do note that when this happens, power dissipation occurs across the device. Here we see a good example of the benefits brought about by integrated current limiting. On the left, we have a waveform of the charge up of a 330 microfarad capacitor to 13.5 volts. We see a supply droop of over 2 volts and a peak inrush current of over 40 amps. Charging this same capacitor to 13.5 volts using TPS-2H160 with a current limit at 3.2 amps gives us the waveform on the right. Here we see the two major benefits of charging capacitors using current limiting. One, there is minimal supply drop, and two, there is low peak current that flows through the device. Therefore, the systems cost that is required for the board is brought down. We will focus more on capacitive charging and thermal behavior in future sections. The next feature that we shall discuss about is the integrated current sensing of TI high-side switches. Similar to the current mirror that is used for current limiting, there exists another current mirror which copies a proportion of the current that flows through the power FET and sends it out of the SNS or CS pin. An external resistor is chosen depending on the range of acceptable voltage for the external ADC or MCU. This voltage can then be processed as needed by any device. Please note that no trimming of sense accuracy is required for TI high-side switches, but the device selection is paramount for best accuracy based on the load current. Like many systems, more information is always preferred. Sensing the current that flows through the power FET of the device provides a lot of clues about the system behavior. Current sensing is usually performed with an inline current sense resistor with an amplifier. This is not required if using TI high-side switches with integrated current sensing. This reduces board cost and solution size. Another benefit is that the SNS output or CS output also doubles as a fault indicator. Please note the different ways that the device depicts a fault. Next, we shall discuss about the inductive load driving capability of TI high-side switches. Offboard loads tend to be inductive in nature. This is either due to the load being a relay or a solenoid, or the fact that long cables themselves can result in significant inductance. This is a natural phenomenon of electromagnetism. As current flows through the wire, this results in a complementary magnetic field, and energy is stored within this magnetic field. When the system is turned off, this energy must be dissipated somewhere. The inductance and the inductor forces current to flow through the circuit. This can be thought of as some form of electric inertia in the circuit. Energy stored is related to the square of the current flow. Therefore, in small inductors, large energies can be held because of the amount of current that is flowing through it. When the load is turned off in an inductive system, the inductor pulls current to maintain the flow. This results in a large negative spike on the output of the high-side switch. If this spike is not clamped, there is a chance that the high-side switch can be damaged. Luckily, TI high-side switches offer an internal clamp to allow for the safe dissipation of inductive energy. We shall focus on inductive load driving and maximum inductive handling in future sections. Open load and short-to-bat detection. Open load and short-to-bat detection enables detection of broken cables or miswiring that could exist in the system. TI high-side switches provide both on-state as well as off-state open load detection. Please note that on-state detection is limited to TPS 1H200 and TPS 1H1000 only. If the load current drops below the threshold that is stated in the datasheet for these devices, the device will automatically register a fault. For all other devices, it is possible to use the current sense output and set a user set limit in the MCU or ADC to detect an on-state open load. Off-state detection is provided by most high-side switches. This requires the diagonal pin to be pulled high and a pull-up resistor between the battery input and the output of the device. If the output voltage is larger than the threshold voltage, then the device recognizes that there is no load attached, ergo an open load during the off state. For TPS-X, HB, XX family of devices, a 1 mega ohm internal pull-up resistor is included, so an external pull-up is not required if the leakage is small. Integrated thermal protection of TI high-side switches. Two major thermal faults can occur in a TI high-side switch. One of them is thermal shutdown and the other is thermal swing. Shutdown or absolute thermal shutdown is when the junction reaches an unsustainable temperature for operation. This results in the device turning off to protect itself during high power or current limiting events. Thermal swing, on the other hand, can be thought of as an interim thermal shutdown because the device does turn off for a little bit. This happens when the FET heats up much faster than the controller of the device. This protects the device from fast thermal events that could damage the power FET before the controller can react. Next, we shall focus on reverse current in the circuit. Reverse current can flow in the circuit due to reverse polarity of the power supply. This is a common mistake in automotive applications if the battery is installed incorrectly. This could damage the device through internal ESD cells becoming forward biased, and there is potential for the MCU or downstream or upstream components to also get damaged. The first protection method for reverse polarity events is the ground network. The ground network consists of a ground resistor and a diode that is placed between IC ground and module ground. This limits the amount of reverse current through the ground resistor, but in normal operation, a lot of power is not consumed because current flows from IC ground through the diode to module ground. Please note that in this situation, ground is shifted by this diode, and the current through the main FET is still unregulated. Following on, in the event an MCU is used, current can flow from the MCU ground through the body diode of the push-pull configuration into the I/O pins of the high-side switch. Therefore, we recommend using a protection resistor which limits the amount of current that flows out of the MCU into the high-side switch. Another method of protection is by adding a blocking diode upstream of the high-side switch. This blocks all reverse paths of current. Please note that power dissipation on the blocking diode is quite high in this situation, and the voltage at the output will be dropped by the diode forward voltage compared to the input voltage of the system.